Alright guys, I'm back to give you one more lesson on triple integrals. I'd like to start by doing a final example of cylindrical coordinates we were talking about in the previous segment, and then we'll move on and talk about spherical coordinates. So here's an example. Let's try to find the volume. Find the volume above z equals x squared plus y squared and below z equals the square root of x squared plus y squared. Okay, of course z equals x squared plus y squared is a paraboloid. In fact, I'm going to draw a picture. That would be a paraboloid, and here's my xyz axes, and here is my paraboloid right here, as usual. Okay, and then we also have the cone z equals the square root of x squared plus y squared that intersects the paraboloid. Let me draw the cone here. The cone would be something like that. And of course, if you set these two equations equal to each other, you'll figure out where the intersection is. Well, the intersection is going to be, so if I set the square root of x squared plus y squared equal to x squared plus y squared, right, then of course I could just think of this as, I could think of this as, in polar coordinates, this is just r, and in polar coordinates, x squared plus y squared is just r squared. And so you find very quickly that r is equal to either 0 or 1, but the point of intersection up here is going to be at a radius of 1. The region that we're looking at is above the paraboloid and below the cone. So I'm kind of shading it in here. Below the cone, so here's the cone, and then the paraboloid is here on the side. And so that is what we're looking at. Okay? So the volume, as we discussed in an earlier video, is just simply the triple integral of dv. But I'm going to set this one up using cylindrical coordinates. And I'm going to put z on the inside. Notice that the paraboloid is underneath the cone, so I'm going to integrate from the paraboloid, which is z equals r squared, up to the cone, which is z equals r. Okay, so dz is on the inside here. And then don't forget that when we're converting to cylindrical coordinates, we have to pay this price, r dr d theta. Okay. If I just look in the xy plane, the region of integration is just going to be basically the projection of this circle. You see, this is just a disk right here at the intersection of the cone and the paraboloid. It just intersects in a circle, and the full circle would have theta from 0 to 2 pi, and it would have r from 0 to 1. Okay, so when we integrate, I'm going to do the theta integration first. Notice that there is no theta anywhere inside these big parentheses. So when I integrate d theta from 0 to 2 pi, I'm just going to get 2 pi, right? I still have to integrate r from 0 to 1. And when I integrate dz, I'm just going to get z, which I evaluate from r down to r squared. So we take r minus r squared for that. Alright, and so what are we left with here? We have 2 pi. The integral, I'm going to multiply this out right now. The r times r is just r squared, so we get 1/3 of r cubed minus 1/4 of r to the 4th. And that has to be evaluated from 0 to 1. Okay, and when you do that, you're going to get 1/3 minus 1/4, which is 1/12. 2 pi times 1/12 is just simply pi over 6. And that is the answer. Clearly, it is a lot easier to do that problem in cylindrical coordinates than it would be in the xy coordinates. Okay, and it's because, again, of the nature of the shape of that region. Both the paraboloid and the cone are very easy to describe when you use cylindrical coordinates. Now, sometimes the symmetry of the shape is such that it's not so much well suited to cylindrical coordinates, but rather spherical coordinates. So this is another coordinate system that we learned about. It's the spherical coordinate system. And I just want to say a quick little bit about spherical coordinates here. If you have a shape that is spherical or part of a sphere, something that has sort of symmetry about the origin rather than just something symmetric along the z-axis, this is a coordinate system that you might want to consider. So cylindrical coordinates are great when your region is symmetric about the z-axis. So if there's, like on this problem, right, the whole symmetry axis, the z-axis, is a beautiful line of symmetry for this whole shape. But in some situations, the symmetry is not so aligned to the axes as it is to just the origin itself. Now, when you're thinking about spherical coordinates, what you're going to have to do is imagine chopping up, your XYZ plane, or space, I should say, in a different way. This is how you chop up little cubes in the XY sense. So like dx would be there, dy would be there, and dz would be there. But when we're doing spherical coordinates, remember that there's a phi, there's an angle phi that we have, there's a radius rho that goes out from the origin, right? And then there's an angle of theta that is with respect to the positive x-axis. So for that, I might, let me just try and see if I can draw this. Here's a little curved piece of this cube here, kind of going, and of course there's a backside to it as well. It's something like that. Okay, so instead of a beautiful rectangular box, dx, dy, dz, these are the dimensions of one of these little differentials of volume with respect to spherical coordinates. The question is, well, how much volume is that? Well, this radial distance here, that is just d rho. Remember that rho is the distance out from the origin to, let's say it's this point right here, and the change in rho is just d rho. All right? On the other hand, this angle right here, this angle is d phi. And if this is an arc of a circle that has a radius of rho, then the actual length of that segment would be rho d phi. Okay? Finally, how long is this side of this cube? Well, we're going to need to know the length of this little section here. If this was rho right here, radially coming out from the origin, and if this is phi right here, the angle, remember that in spherical coordinates the angle is measured down from the vertical z-axis, this becomes rho sine phi, right? If you think about trigonometry, the hypotenuse of the triangle is rho, the angle is phi, so this becomes rho sine phi. And now we're looking at a little section of the arc of that circle. So imagine a circle going horizontally around the z-axis right there, right? That has a angle measure of d theta, right? So we can think of this as just a flat circle whose radius is rho sine phi, and we're looking at an arc of that circle where the angle is d theta. So how long is that going to be? That segment is going to be rho sine phi d theta. Okay, this is approximately you know, assuming that the d rho, d phi, and d theta are very small, this is approximately a box. And the dimensions of the box are, of course, the total amount of the box is the volume dv, but it has, you know, one side of length d rho, another side of length rho d phi, and another side of length rho sine phi d theta. In other words, the volume here is rho squared sine phi d rho d phi d theta. And so just as you have to pay a little bit of a price when you convert to cylindrical coordinates or polar coordinates, right? The r dr d theta, right? Just as you have to do that, when we convert to spherical coordinates, there's also a price we have to pay, and you're going to want to memorize this one. It's just rho squared times the sine of phi. Let me give you a couple of quick examples, and then I'm going to call it good. For the first example, let's find the formula. Maybe you already know this formula. It's the formula for the volume of a sphere. Find the formula for the volume of a sphere of radius little a. Now, we're talking about a sphere. So, spherical coordinates would be a reasonable choice to use for finding the volume here. Okay? So this is my region, or my solid 3-space E. So the volume is just the triple integral over E of dV. Okay? And what I'm going to do is set that up in spherical coordinates. I know that I have to replace dV with rho squared sine phi, and then I'm going to do d rho, d phi, d theta. This is normally the order of integration that is used for spherical coordinates, but it doesn't have to be that. Since we're doing the whole sphere, theta is going to go all the way from 0 to 2 pi. Phi is going to go all the way from 0 to pi. And rho is going to go all the way from the origin out to the edge of the sphere. And again, the radius is a, so the upper limit of that integration would be a. Let's try to do this integration. When I do the theta integral, notice that there's no thetas anywhere inside the two inside integrals. So integrating d theta from 0 to 2 pi is just going to give me 2 pi. All right? I still have the phi integral here from 0 to pi. I'll put my sine of phi right there. And then what else do I have? Well, I just have the integral of rho squared. That's going to give me 1/3 of rho cubed. But notice I'm going to be evaluating rho cubed between 0 and a, and it's just going to give me a cubed. It's just going to give me a cubed when I evaluate at the limit of a. So what do I have? I have 2 pi over 3 times a cubed. And finally, I have to just do the integral of the sine of phi, which is negative the cosine of phi, evaluated from 0 to pi. And when you do that, you can check very easily that the answer is just simply going to be 2. So this evaluation gives you 2, and so your final answer here is just 4 pi over 3 times a cubed. You might have seen that formula in a geometry class. That's the formula for the volume of a sphere, and we've derived it now using spherical coordinates. Let me give you one final example. This time I'm just going to state it as an evaluation. Evaluate the integral from -3 to 3 of the integral from negative radical 9 minus x squared to radical 9 minus x squared, and then integral from 0 to radical 9 minus x squared minus y squared of z times the square root of x squared plus y squared plus z squared dz, dy, dx. Let's see if we can solve this triple integral. Okay? Hopefully you guys can see that all right. Now, what I would recommend, if you look on the outside, you have your x and y variables. So I always like to label, this is x, this one is y, and that means the inside one would have to be z. I'm seeing a lot of things here that suggest spherical coordinates to me. Right? First of all, x squared plus y squared plus z squared, we know that that is just rho squared. Okay, and also if we just look in the xy plane, notice that x goes from -3 to 3. And what do we have here for the equation for y? Well, x squared plus y squared is supposed to be 9. So that's just a circle. So here's the circle. So you have a circle right here. You have a circle right here. And we're looking at z starting at 0 and going to the top of this equation. This right here, if you set this equal to z, this turns into the equation of a sphere of radius 3. In other words, the three-dimensional picture is simply the top half of a hemisphere. All right. That kind of a shape is well suited to spherical coordinates. It's a hemisphere of radius 3. It's the top half because z starts at 0 and goes up from there. The x and y domain is exactly this circle. So let's convert it into spherical coordinates. This is going to be so much nicer. Theta just goes from 0 to 2 pi. Phi is only going to go from 0 to pi over 2 because we only are looking at the top half of that sphere. And then rho has to go from 0 to 3, which is the radius of this hemisphere. Okay, then I need to replace the integrand. Z in spherical coordinates, z is rho cosine phi. Okay. In spherical coordinates, that radical just becomes rho. We have our price we have to pay for converting to spherical coordinates, which I derived earlier in this video. It's just rho squared sine phi. You always have to throw that in there. And then d rho, d phi, d theta. This is your integral. As with the last example, I can put the 2 pi for the theta integration right away. The outside integral, there's no thetas anywhere on the inside part of this integration. Okay? Then I'm going to integrate phi from 0 to pi over 2. The function that we have, where we have the phi, what do we have? We have cosine of phi, we have sine of phi. Okay, so I'll write that down. And then I have 1, 2, 3, 4 factors of rho. When I integrate 4 factors of rho, I'm going to get 1/5 of rho to the 5th, which will just be 3 to the 5th once I'm done evaluating it. Okay, so we have, let's take some of these constants onto the outside. I have 2 pi over 5. 3 to the 5th is 243. When I integrate cosine times sine, I can just use a u substitution. It's going to give me 1/2 of sine squared of phi. And that's just going to give me 1/2 when I evaluate this. So the answer is 243 pi over 5. Okay. That's a couple of examples of problems that can be solved in spherical coordinates. I'm going to encourage you guys to practice this a lot. Go over the video again if you need to and try some more problems, and I'll be happy to answer questions on this as soon as we get back together again. Thanks a lot for watching.